A binomial expression is the sum or difference of two terms. So, for example, 2x plus 3y is an example of a binomial expression because it's the sum of the term 2x and the term 3y. It's the sum of these two terms. Some of the terms could be just numbers. So, for example, x plus 1 is the sum of the term x and the term 1, so that too is a binomial expression. A minus b is the difference of the two terms a and b, so that too is a binomial expression. Now, in your previous work, you'll have seen many binomial expressions and you'll have raised them to different powers, so you'll have squared them, cubed them, and so on. You'll probably already be very familiar with working with the binomial expression like x plus 1 and squaring it. And you'll have done that by remembering that when we want to square a bracket, we're multiplying the bracket by itself. So x plus 1 squared is x plus 1 multiplied by x plus 1. And we remove the brackets by multiplying all the terms in the first bracket by all the terms in the second bracket, so there'll be an x multiplied by x, which is x squared, x multiplied by 1, which is just x, 1 multiplied by x, which is another x, and 1 multiplied by 1, which is just 1. So to tidy all that up, x plus 1 squared is equal to x squared. There's an x plus another x, which is 2x, plus the 1 at the end. Note in particular that we have 2x here, and that came from this x here and another x there. I'll come back to that point later on, and we'll see why that's important. Now, suppose we want to raise a binomial expression to a power that's higher than 2. So suppose we want to cube it, raise it to the power 4 or 5 or even 32. The process of removing the brackets by multiplying term by term over and over again is very, very cumbersome. I mean, if we wanted to work out x plus 1 to the 7, you wouldn't really want to multiply a pair of brackets by itself several times. So what we want is a better way of doing that. And one way of doing it is by means of a triangle of numbers, which is called Pascal's triangle. Pascal was a 17th century French mathematician, and he derived this triangle of numbers that we'll repeat for ourselves now. And this is how we form the triangle. We start by writing down the number 1. Then we form a new row, and on this new row we have a 1 and another 1. We're going to build up a triangle like this, and each new row that we write down will start with a 1 and will end with a 1. So my third row is going to begin with a 1 and end with a 1, and in a few minutes we'll write a number in there, in the gap. The next row will begin with a 1 and end with a 1, and we'll write a number in there and a number in there. And in this way we can build a triangle of numbers, and we can build it as big as we want to. How do we find this number in here? Well, the number that goes in here we find by looking on the row above and looking above to the left and above to the right and adding what we find. There's a 1 here, there's a 1 there, we add them, 1 and 1 gives 2, and we write the result in there. So this 2 on the third row has come by adding that 1 and that 1 together. Let's look at the next row down. The number that's going to go in here is found by looking on the previous row, and we look above left, which gives us the 1. We look above to the right, which gives us 2, and we add the numbers that we find. So we're adding a 1 and 2, which is 3, and we write that in there. What about the number here? Well, again, previous row, above to the left is 2, above to the right is 1, we add what we find. 2 plus 1 is 3, and that goes in there. And we can carry on building this triangle as big as we want to. Let's just do one more row. We start the row with a 1, and we finish with a 1, and we put some numbers in here, and in here, and in here. The number that's going to go in here is found from the previous row by adding the 1 and the 3. So 1 plus 3 is 4, and we write that in there. The number that's going to go in here, well, we look in the previous row above left and above right. 3 plus 3 is 6, and we write that in there. And finally, 3 plus 1 is 4, and we write that in there. So that's another row. And what you should do now is practice generating additional rows for yourself. And altogether, this triangle of numbers is called Pascal's triangle. Okay. Now we're going to use this triangle to expand binomial expressions, and we'll see that it can make life very easy for us. We'll start by going back to the expression a plus b to the power 2. So we have a binomial expression here, a add b, and we're raising it to the power 2. Let's do it the old way, first of all, by multiplying a add b by itself, because we're squaring a add b. Let's write down what we'll get. A multiplied by a gives us a squared. A multiplied by b will give us a times b, or just ab. B multiplied by a gives us a ba. And finally, b multiplied by b gives us a b squared. And if we just tidy up what we've found, there's a squared. There's an ab, and because ba is the same as ab, there's another ab here. So altogether, there's 2 lots of ab. And finally, a b squared at the end. Now that's the sort of expansion, the sort of removing brackets that you've seen many times before, you're already very familiar with. But what I want to do is make some observations about this result. When we expanded a plus b to the power 2, what we find is that as we successively move through these terms that we've written down, the power of a decreases. It starts off here with an a squared, the highest power being 2, corresponding to the power in the original binomial expression. And then every subsequent term, that power drops. So it was a to the power 2. There's a to the power 1 in here, although we don't normally write the 1 in. And then no a's at all. So the powers of a decrease as we move from left to right. What about b's? There's no b's in here. There's a b to the 1 in there, although we just normally write b, and a b to the power 2 there. So as we move from left to right, the powers of b increase until we reach the highest power, b squared, and the squared corresponds to the 2 in the original problem. What else can we observe? If we look at the coefficients of these terms, now the coefficients are the numbers in front of each of these terms. Well, there's a 1 in here, although we wouldn't normally write it in. There's a 2 there, and there's a 1 in front of the b squared, although we wouldn't normally write it in. So the coefficients are 1, 2, and 1. Now let me remind you again about Pascal's triangle. I have a copy of the triangle here so we can refer to it. If we look at Pascal's triangle here, we'll see that 1, 2, 1 is the numbers that's in the third row of Pascal's triangle. 1, 2, 1 are the numbers that occur in the expansion of a plus b to the power 2. There's something else I want to point out. That this 2ab in here came from a term here, 1ab, and 1ba in there. And together the 1 plus the 1 gave the 2. in exactly the same way as the 2 in Pascal's triangle came from adding the 1 and the 1 in the previous row. So Pascal's triangle will give us an easy way of evaluating a binomial expression when we want to raise it to an even higher power. Let me look at what happens if we want a plus b to the power 3. And we'll see that we can do this almost straight away. What we note is that the highest power now is 3, so we start with an a to the power 3. Each successive term, that power of a will reduce. So there'll be a term in a squared, there'll be a term in a, and then there'll be a term without any a's in at all. So as we move from left to right, the powers of a decrease. Similarly, as we move from left to right, we want the powers of b to increase, just as they did here. There'll be no b's in the first term. There'll be b to the power 1, or just b, in the second term, b to the power 2 in the next term, and then finally there'll be a b to the power 3, and we stop at b to the power 3, that highest power corresponding to the power in the original binomial expression. We need some coefficients. That's the numbers in front of each of these terms. And the numbers come from the relevant row in Pascal's triangle. And we want the row that begins 1, 3. And the reason why we want the row beginning 1, 3 is because 3 is the power in the original expression. So I go back to my Pascal's triangle, and I look for the row beginning 1, 3, which is 1, 3, 3, 1. So these numbers are the coefficients that I need in this expansion. I want 1, 3, 3, and 1. And just to tidy that up a little bit, 1a cubed would normally just be written as a cubed, 3a squared b, 3ab squared, and finally 1b cubed, which we'd normally write as just b cubed. Now, I hope you'll agree that using Pascal's triangle to expand a plus b to the power 3 is much simpler than multiplying a plus b times a plus b times a plus b. What I want to do for just before we go on is just actually go and do it the long way, just to point something out. Let's go back to a plus b to the power 3 and work it out the long way by noting that we can work this out as a plus b multiplied by a plus b all squared. We've already expanded a plus b to the power 2, so let's write that down. Well, remember, a plus b to the power 2, we've already seen, is a squared, 2ab, and b squared. Now, to expand this, everything in the first bracket must multiply everything in the second bracket. So we've an a multiplied by a squared, which is a cubed. A multiplied by 2ab, which is 2a squared b. A multiplied by b squared, which is a b squared. We've b multiplied by a squared, which is ba squared. We've b multiplied by 2ab, which is 2ab squared. And finally, a b multiplied by a b squared is a b cubed. To tidy this up, there's a cubed, and then notice there's a squared b terms in here, and there's also an a squared b term there, one of them. So with a 2 there and a 1 there, 2 and the 1 gives you 3 lots of a squared b. There's an a b squared here, and there's more a b squareds there. There's 1 there, 2 of them there. So altogether, we'll have 3 lots of a b squared. And finally, the last term at the end, b cubed. That's working out the expansion the long way. Why have I done that? Well, I've only done that just to point out something to you. And I want to point out that the 3 in here, in the 3a squared b, came from adding a 2 here and a 1 in there. 2 plus the 1 gave you the 3. Similarly, this 3 here came from a 1 lot of ab squared there and 2 lots of ab squared there. So the 1 plus the 2 gave you the 3. And that mirrors exactly what we had when we generated the triangle, because the 3 here came from adding the 1 and the 2 in the row above, and the 3 here came from adding 2 and 1 in the row above. Let's have a look at another example and see if we can just write the answer down straight away. Suppose we want to expand a plus b all raised to the power 4. Well, this is straightforward to do. We know that when we expand this, our highest power of a will be 4, because that's the power in the original expression. And thereafter, every subsequent term will have a to a power reduced by 1 each time. So there'll be an a cubed, an a squared, an a, and then no a's at all. As we move from left to right, the powers of b will increase. There'll be none at all in the first term, and there'll be a b to the 1, or just b, a b to the 2, b to the 3, or b cubed, and finally the last term will be b to the 4, and again the highest power corresponding to the power 4 in the original expression. And all we need now are the coefficients. The coefficients come from the appropriate row in the triangle, and this time, because we're looking at power 4, we want to look at the row beginning 1, 4. The row beginning 1, 4 is 1, 4, 6, 4, 1. Those are the coefficients that we'll need. 1, 4, 6, 4, 1. And just to tidy it up, we wouldn't normally write the 1 in there and the 1 in there. So a add b to the 4 is a to the 4, 4a cubed b, that's that term, 6a squared b squared, 4ab cubed, and finally b to the power 4. Okay, so I hope you'll agree that using Pascal's triangle to get this expansion was much simpler than multiplying this bracket over and over by itself lots and lots of times. That way is also prone to error, so if you can, get used to using Pascal's triangle. We can use the same technique even when we've slightly more complicated expressions. Let's do another example. Suppose we want to expand 2x plus y all to the power 3. So it's more complicated this time because I just haven't got a single term here, but I've actually got a 2x in there. The principle is exactly the same. What we'll do is we'll write this term down first, the whole of 2x, and just like before, it'll be raised to the highest possible power, which is 3, and that corresponds to the 3 in the original problem. Every subsequent term will have a 2x in it, but as we go from left to right, the power of 2x will decrease. So the next term will have a 2x all squared. The next term will have a 2x to the power 1, or just 2x, and then there won't be any at all in the last term. Powers of y will increase as we move from the left to the right. So there won't be any in the first term, then there'll be y, then there'll be y squared, and finally y cubed. And then we remember the coefficients. Where do we get the coefficients from? Well, because we're looking at power 3, we go to Pascal's triangle and we look for the row beginning 1, 3. You might even remember those numbers now. We've seen it so many times. The numbers are 1, 3, 3, 1. Those are the coefficients we require. 1, 3, 3, 1. So I want one of those, 3 of those, 3 of those, 1 of those. And there's just a bit more tidying up to do to finish it off. Here we've got 2 to the power 3, 2 cubed. That's 8. X cubed. And the 1 can just stay there. 1 multiplied by all that is not going to do anything else. It's just 8x cubed. What about this term? There's a 2 squared, which is 4. And it's got to be multiplied by 3. So 4 3s are 12. So we'll have 12. What about powers of x? Well, there'll be an x squared, y. In this term, we've just got 2x to the power 1. That's just 2x. So this is just 3 times 2x, which is 6x, and there's a y squared. And finally, there's just the y cubed at the end. 1y cubed is just y cubed. So there we've expanded the binomial expression 2x plus y to the power 3 in just a couple of lines using Pascal's triangle. Let's look at another one. Suppose this time we want 1 plus p, different letter, just for a change, 1 plus p all raised to the power 4. In lots of ways, this is going to be a bit simpler, because as we move through the terms from left to right, we want powers of the first term, which is 1. We want 1 to the power 4, 1 to the power 3, 1 to the power 2, and so on. But 1 to any power is still 1, so that's going to make life easier for ourselves. So 1 to the power 4 is just 1, and then thereafter there'll be just 1 all the way through. We want the powers of p to increase. We don't want any p's in the first term. We want a p there, p squared there. The next term will have a p cubed in, and the last term will have a p to the 4 in. These 1s are the powers of the first term 1. So 1 to the 4, 1 to the 3, 1 to the 2, 1 to the 1, which is just 1, and no 1s there at all. And finally, we want some coefficients. And the coefficients come from Pascal's triangle, this time the row beginning 1, 4, because of this power 4 here. So the numbers we want are 1, 4, 6, 4, 1. 1, 4, 6, 4, and 1. Let's just tidy it up. There's 1. 4 times 1 is just 4p. 6 times 1 is 6, 6p squared. 4 times 1 is 4, p cubed. And last of all, 1 times p to the 4 is just p to the 4. Again, another example of a binomial expression raised to a power, and we can almost write the answer straight down using the triangle, instead of multiplying those brackets out over and over again. Now sometimes, either or both of the terms in the binomial expression might be negative. So let's have a look at an example where one of the terms is negative. So suppose we want to expand 3a minus 2b, so I've got a term that's negative now, minus 2b, and let's suppose we want this to the power 5. 3a minus 2b, all raised to the power 5. This is going to be a bit more complicated this time, so let's see how we get on with it. As before, we want to take our first term and raise it to the highest power being 5. So our first term will be 3a, all raised to the power 5. The next term will have a 3a in it, and this time it'll be raised to the power 4. There'll be another term with a 3a in it, and it'll be 3a to the power 3, then 3a to the power 2, then 3a to the power 1, and then there'll be a final term that doesn't have 3a in it at all. That deals with this first term. Let's deal with the minus 2b now. In the first term here, there won't be any minus 2b's at all, but thereafter, the powers of this term will increase as we move from left to right, exactly as before. So when we get to the second term here, we'll need a minus 2b. When we get to the next term, we'll need minus 2b, and we're going to square it. Minus 2b raised to the power 3. Minus 2b raised to the power 4. And the last term will be minus 2b raised to the power 5. The power 5 corresponding to the highest power in the original problem. We also need our coefficients, the numbers in front of each of these 6 terms. The coefficients come from the row beginning 1, 5, because the problem has a power 5 in it. The coefficients are 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. So we want 1 of those, 5 of those, 10 of those, 10 of those, 5 of those, and finally 1 of those. You can see now why I left a lot of space when I was writing all this down. There's a lot of things to tidy up in here. Just to tidy all this up, we need to remember that when we raise a negative number to, say, the power 2, the result's going to be positive. When we raise it to an even power, the result will be positive. So this term is going to be positive, and the minus 2b to the power 4 will also become positive. When we raise it to an odd power, like the 3 or the 5, the result's going to be negative. So our answer is going to have some positive and some negative numbers in it. Let's tidy it all up. I've got a calculator for this because I'm going to raise some of these numbers to some powers. First of all, I want to raise 3 to the power 5. 3 to the power 5 is 243. So I'll have 243, a to the power 5, and it's all multiplied by 1, which isn't going to change anything. Now here, we've got a negative number, because this is minus 2b raised to the power 1. It's going to be negative, so this term is going to have a minus sign at the front. We've got 3 to the power 4. Well, I know 3 squared is 9, and 9 nines are 81, so 3 to the power 4 is 81. 5 twos are 10, so I'm going to multiply 81 by 10, which is 810. There'll be a to the power 4 and a single b. So that's my next term. Now what have we got left? There's 3 to the power 3, which is 3 cubed, which is 27, multiplied by 2 squared, which is 4, all multiplied by 10, which is 1080. A to the power 3, b to the power 2. And here we have 2 cubed, which is 8, 3 squared, which is 9, 9 eighths are 72, multiplied by 10 is 720. There'll be an a squared from this term, and there'll be a b cubed from the last term. What about here? Well, we've 2 to the power 4, which is 16. 5 threes are 15 here, and 15 multiplied by 16 is 240. It'll be positive because here we have a negative number to an even power. 240, a to the power 1, or just a, b to the power 4. And finally, there'll be one more term, and that will be minus 2 to the power 5, which is going to be negative 32 b to the power 5. And that's the expansion of this rather complicated expression which had both positive and negative quantities in it. And again, we've used Pascal's triangle to do that. We can use exactly the same method even if there are fractions involved. So let's have a look at an example where there's some fractions. Suppose we want to expand, this time 1 plus 2 over x, so I've deliberately put a fraction in there, all to the power 3. Let's see what happens. One plus 2 over x to the power 3. Well, we start with 1 raised to the highest power, which is 1 to the power 3, which is still 1. And 1 to any power will still be 1 as we move all the way through the calculation. We'll have 2 over x raised, first of all, to the power 1, two over x to the power 2, and 2 over x to the power 3, and we stop there when we reach the highest power, which corresponds to the power in the original problem. We need the coefficients of each of these terms from Pascal's triangle, and the row in the triangle beginning 1, 3. Those numbers are 1, 3, 3, 1. So there's 1 of these, 3 of those, 3 of those, and 1 of those. And all we need to do now is tidy up what we've got. So there's 1. 2 over x to the power 1 is just 2 over x. We're going to multiply it by 3. So 3 2s are 6. We'll have 6 divided by x. Here there's a 2 squared, which is 4, and we're multiplying it by 3. So we have 12 divided by x to the power 2 divided by x squared. And finally, there's 2 to the power 3, which is 8. And this time it's divided by x to the power 3, or x cubed. So that's a simple example which illustrates how we can apply exactly the same technique even when there are fractions involved. Now that's not quite the end of the story. The problem is, supposing I were to ask you to expand a binomial expression to a very large power. Suppose I wanted 1 plus x to the power 32, or 1 plus x to the power 127. You'd have an awful lot of rows of Pascal's triangle to generate if you wanted to do it this way. Fortunately, there's an alternative way, and it involves a theorem called the binomial theorem. So let's just have a look at what the binomial theorem says. The binomial theorem allows us to develop an expansion of the binomial expression a plus b raised to the power n, and it allows us to get an expansion in terms of decreasing powers of a, exactly as we've seen before, and increasing powers of b, exactly as we've seen before. And I'm going to quote the theorem for the case when n is a positive whole number. This theorem will actually work when n is negative and when it's a fraction, but only under exceptional circumstances, which we're not going to discuss here. So in all these examples, n will be a positive whole number. Now what the theorem says is this, that a plus b to the power n is given by the following expansion. A to the power n. Now that looks familiar, doesn't it? Because as in all the examples we've seen before, we've taken the first term and raised it to the highest power, the power in the original question, a to the power n. Then there's a next term, and the next term will have an a to the power n minus 1 and a b in it That's exactly as we've seen before, because we're starting to see the terms involving b appear, and the powers of a are decreasing. We want a coefficient in here, and the binomial theorem tells us that the coefficient is n. The next term has an a to the power n minus 2 in it, along with the line we had before of decreasing the powers, and increasing the power of b will give us a b squared. And the binomial theorem tells us the coefficient to write in here, and the coefficient this time is n minus 1 over 2 factorial. In case you don't know what this notation means, 2 factorial means 2 times 1. That's called 2 factorial. And this series goes on and on and on. The next term will be n minus 1, n minus 2 over 3 factorial. And there's a pattern developing here. You see here we had an n minus 1, n minus 1, n minus 2, with a 3 factorial at the bottom, whereas we had a 2 factorial at the bottom before. 3 factorial means 3 times 2 times 1. The power of a will be 1 less again, which this time will be a to the n minus 3. And we'll want a power of b, which is b to the power 3. So all the way through this theorem, you'll see the powers of a are decreasing and the powers of b are increasing. Now this series goes on and on and on until we reach the term b to the power n when it stops. So this is a finite series. It stops after a finite number of terms. Now, the theorem's often quoted in this form, but it's also often quoted in a slightly simpler form. And it's quoted in the form for which a is the simpler value of just 1 and b is x. Now, when a is 1, all of these a to the power n's, or a to the n minus 1, a to the n minus 2, each one of those terms will just simplify to the number 1. So the whole thing will look simpler. So let's write down the binomial theorem again for the special case when a is 1 and b is x. This time we'll get 1 plus x raised to the power n is equal to 1 plus n x plus n minus 1 over 2 factorial x squared. And you can see what's happening. This second term x is starting to appear, and its power is increasing as we move from left to right. So we have an x squared. The next term will have an x cubed in it. 1 to any power is still 1, so I don't actually need to write it down. The next term will be n minus 1, n minus 2 over 3 factorial x cubed. The next term will be n minus 1, n minus 2, n minus 3 over 4 factorial x to the 4. And this will go on and on until eventually you'll get to the stage where you'll get to the last term raised to the highest power. You'll get to x to the power n, and the series will stop. So this is a slightly simpler form of the theorem, and it's often quoted in this form. Now let's use it to examine some binomial expressions that you're already very familiar with. Let's suppose we want to expand 1 plus x all raised to the power 2. Now I've written down the theorem again so we can refer to it, and this is printed in the notes if you want to use the one in the notes. So we've 1 plus x to the power n. In our problem we've got 1 plus x to the power 2. So all we have to do is let n be 2 in all of this formula through here. So let's see what we get. Well, from the theorem, the first thing we'll write down is just the 1. Then we want nx, but n is 2, so we'll just put plus 2x. And then the next term we want is going to be a term involving x to the power 2. But that's the highest power we want because we've got a power 2 in here. We want to stop when we get to x to the power 2, so we're actually already at the end with the next term, and we just want an x to the power 2 on its own. 1 plus 2x plus x squared. And that's the expansion that you're already very familiar with. And you'll notice in it that the powers of x increase as we move through from left to right, and there's powers of 1 in there, but we don't see them. And the 1, 2, 1 are the numbers in Pascal's triangle. Let's look at the theorem for the case when n is 3. Let's expand 1 plus x to the power 3. I'm going to use the theorem again, but this time we're going to let n be 3. So we'll want 1 plus 3x and then we'll want 3 minus 1. 3 minus 1 is 2, all divided by 2 factorial, then an x squared. And then the next term will be a term involving x cubed, which is the term that we stop with because we're only working to x to the power 3 here. So the last term will be just a plus x cubed. We can tidy this up to 1 plus 3x. 2 factorial is 2 times 1, which is just 2. It'll cancel with the 2 at the top, so we'll be left with just 3, x squared, and finally an x cubed. And again, that's something that you're already very familiar with. You'll notice the coefficients, the 1, 3, 3, 1, are the numbers we've seen many times in Pascal's triangle. The powers of x increase as we move from the left to the right, and this is a finite series. It stops when we get to the term involving x cubed, corresponding to this highest power over there. Now, let's suppose we want to look at a more complicated problem. Suppose we want to work out 1 plus x to the power 32. Now, you'd never use Pascal's triangle to attempt this problem because you'd have to generate so many rows of the triangle. But we can use the binomial theorem. What I'm going to do is I'm going to write down the first 3 terms of the series using the binomial theorem. I'm going to use it with n being equal to 32. So we're putting n is 32 in the theorem. We'll get 1 plus 32x, that's the 1 plus the nx. We want n, which is 32, n minus 1, which will be 31, all over 2 factorial x squared. And we know that this series will go on and on until we reach the term, the last term, being x to the power 32. But I only want to look at the first 3 terms here in this problem. So the first 3 terms are just going to be 1 plus 32x, and we want to simplify this. We've got 32 multiplied by 31 and then divided by 2, which is 496. And I just put some dots there to show that this series goes on a lot further than the terms that I've just written down there. We're going to have a look at a couple more examples. With some ingenuity, we can use the theorem in a slightly different form. Suppose we want to expand this binomial expression. This time I'm going to look at 1 plus y divided by 3, all raised to the power 10. And suppose that I'm interested in generating the first 4 terms. Let's see how we can do that. Well, we've got our theorem. I've written it down again here for us in terms of 1 plus x to the power n. We can use it in this problem if we replace every x in the theorem with a y over 3. So everywhere there's an x in the theorem, I'm going to write y divided by 3. And then the pattern will match exactly what we have in the theorem. N's going to be 10 in this problem. So let's see what we get. We'll have 1 plus y over 3 raised to the power 10 is equal to, well, we start with a 1, as always. Then we'll want nx. N is 10. And we said that instead of x, we're replacing the x with a y over 3. So we'll have a y over 3 there. What's the next term? We'll want n minus 1 over 2 factorial, which is 10. 10 minus 1 is 9 over 2 factorial. And then we'd want an x squared. So in this case, we'll want x being y over 3, all squared. I want to generate one more term because I've said I want to look for 4 terms. So the next term is going to be n, which was 10, n minus 1, which is 9, n minus 2, which is 8, and this time over 3 factorial. So I'm here, n minus 1, n minus 2 over 3 factorial, and we want x cubed. X is y over 3, so we want y over 3 cubed. And the series goes on and on. Let's just tidy up what we've got. There's 1. There'll be 10y over 3. What have we got in here? Well, there's a 3 squared at the bottom, which is 9, and there's a 9 at the top. So the 3 squared in here is going to cancel with the 9 there. 2 factorial is just 2, and 2 into 10 is 5. So we'll have 5y squared. And then this is a bit more complicated. We've got a 3 factorial, which is 3 times 2, and 3 cubed at the bottom there, which is 3 times 3 times 3. Some of this will cancel down. 3 times 3 will cancel with the 9 in here. The 2 will cancel there with the 8, and we'll have 4. And let's see what we're left with. At the top, we'll have 10 multiplied by 4, which is 40. And at the bottom, we'll have 3 multiplied by 3, which is 9. And there'll be a y cubed. So altogether, we've 1 plus 10y over 3, 5y squared, and 40 over 9y cubed. And those are the first 4 terms of a series which will actually continue until you get to a term involving the highest power, which will be a y over 3 to the power 10. So you can still use the theorem in slightly different form if you use a bit of ingenuity. I want to look at one final example before we finish. And this time I want to look at the example 3 minus 5z to the power 14. Again, it's an example where you wouldn't want to use Pascal's triangle because the power 14 is too high and you'd have too many rows to generate in your triangle. I'm going to use the original form of the theorem, the one I have here in terms of a plus b to the power n. A will be 3. Now b is a negative number. B will be minus 5z. N's going to be 14. But we can still use the theorem. Let's see what happens. And in this problem, I'm just going to generate the first 3 terms. OK. So A is 3. And we want to raise the 3 to the highest power, which is 14. So my first term is 3 to the power 14. My second term is this one. Begins with an n. The power in the original expression, which was 14, multiplied by a to the power n minus 1. A is 3, and we want to raise it to the power n minus 1. 14 minus 1 is 13, and we want a b. B is minus 5z. So our second term, looking ahead, is going to be negative because of that minus 5 in there. My third term, and I'll stop after the third term, is n which is 14, n minus 1, which is 13, all over 2 factorial, a to the power n minus 2 will be 3 to the power n minus 2 will be 14 minus 2, which is 12. And finally a b, which was minus 5z, raised to the power 2. And we know this goes on and on until we reach a term in z to the power 14. But we've only written down the first 3 terms there. Perhaps we should just tidy it up a little bit. There's a 3 to the power 14 at the beginning. There's a minus 5 here. Minus 5 14s are minus 70. There's a 3 to the power 13. Let me just leave it like that for the time being. And then there'll be a z. Over here, there's a 3 to the power 12. That's this term in here. And I'm reaching for my calculator again because this is a bit more complicated. We have got a 14 multiplied by a 13. We're multiplied by 5 squared, which is 25, and divided by the 2 factorial, that's divided by 2. This will be multiplied by 2275. And this expression will be positive because we've got a minus 5 squared, and we need to remember to include a z squared in there. Okay, we observe as before that the powers of z are increasing as we move from the left to the right. Now we could leave it like that. I'm just going to tidy it up and write it in a slightly different form because this is often the way you see answers in the back of textbooks, or people ask you to give an answer in a particular form. And the form I'm going to write it in is one obtained by taking out a factor of 3 to the power 14. If I take a 3 to the 14 out from the first term, I'll be just left with 1. Now I have 3 to the 13 in the second term, but if I multiply top and bottom by 3, I'll have a 3 to the 14 at the top, which I can take out. But I've multiplied the bottom by 3 as well, which will leave me with minus 70z divided by 3. Here we have a 3 to the power 12, and I want to take out a 3 to the 14. If I multiply the top and bottom by 3 squared, or 9, I effectively get a 3 to the 14 in this term. So I'm multiplying top and bottom by 9, taking the 3 to the 14 out, and that will leave me here with 2275 over 9 z squared. And this series continues, as I said before, until you get to a term involving z to the power 14. But those are the first 3 terms of the series.